the impulse momentum theorem. We will look at Newton's force law and look at events that occur at an instant, in particular collisions and explosions. We'll define impulse and momentum and then look at the impulse momentum theorem. We'll see when we can then use conservation of momentum, and we'll discuss different types of collisions, in particular the elastic and inelastic cases. In doing so, we will revisit the center of mass concept. So first off, we're looking at events that occur in a brief moment, for example, a collision. Now, there was a car accident, a fender bender. You can see their front ends are crumpled in. And what's important is to think of this collision or an explosion as there's a before, where the two cars are traveling toward each other and they're just about to hit, right? So just about to collide. Then during, right? Then there's the actual collision where the front ends are crumpling in. It all maybe takes a fraction of a second. And then the after effect. In this case, the cars are now at rest and their front ends are deformed. And these are the three states we're interested in. There's a before, objects just about to collide. There's a process that involves very large contact forces between the objects over a short amount of time. And then the collision's over, and the objects have experienced a deformation of their structure and had a change in internal energy. Now, next we look at impulse and momentum. So, starting with the force law, if we write the acceleration as the time rate of change of velocity and multiply both sides by a time element dt, on the left we get Newton seconds, we get what we'll call impulse. And on the right side, we'll bring mass into the in with velocity and say that we have a differential change in mass times velocity, and we'll call mass times velocity momentum. Now, for not an infinitesimal, but for a finite but very small time, like think of a collision or explosion, the time could be a fraction of a second. We'll just replace the infinitesimals with finite changes. And in that case, the force then is like an average force over that time. In any case, this is the impulse momentum theorem. It's an alternative to the force law. It basically says that the impulse delivered to an object equals the change in momentum of the object. And as we said, that will be useful for collisions. And let's look at conservation of momentum. So here's two objects, they collide, they move on their separate ways. Unlike the car accident, the two objects in this example went their separate ways. But in either case, there is the before picture, the objects about to collide. There's the actual collision. And then there's the after picture, where in this case the objects are now leaving the scene in different directions and different velocities. Now, it turns out that whereas we always have the impulse momentum theorem, if we include as the object of interest all of the objects involved in the collision, then those large contact forces between those objects, they're internal, right? So if we include all of the participants in the collision, then the impulse is that delivered by the surroundings, which would be almost zero, right? We would have finite forces on the order of an object's weight times a very, very small time, and we can generally ignore that in most cases. In some cases, there is no impulse what have you, like this could be two things colliding in space. But even if they're colliding in midair, the weight of the objects times a microsecond can be neglected. And what we would get is 0 equals change in momentum, or the total initial momentum is equal to the final momentum. And what's implied here is a vector sum over all of the objects involved in the collision. So the conservation of momentum, we just have to make sure we included everything that was involved in that collision. Now, we already saw the car accident case where the objects were stuck, they were either stuck together or just sitting there at rest waiting for the police to show up, or those bouncy balls in the second case that bounced off each other. We can discuss a range of collisions and learn about the terms elastic and inelastic collisions. So I like to think of a sliding scale, epsilon, that goes from 0 to 1. And you can think of all collisions as being a level on that scale. Now, if the objects stick together, or they are at least moving at the same velocity, even if that velocity is 0, like the car accident case, we call that the completely or perfectly inelastic case. Right? So there's before each object is moving at a different velocity, then they collide and they're either stuck together or not stuck together but moving at the same velocity, or 0. Right? So that's the completely inelastic end of the scale. On the other end of the scale is the elastic collision, and that was the case with the red and the blue balls that collided and went their separate ways. Right? If those balls were, like, if you remember having a bouncy ball, perfectly bouncy, then we would not only conserve momentum, but we can also conserve kinetic energy. Now, in practice, all real collisions are inelastic. There is nothing perfectly bouncy such that we can conserve kinetic energy, except for questions that we will say so, right? So, the idea of an inelastic collision, that's where epsilon is between 0 and 1, but not 1, but it could be 0, right? The completely inelastic case is a special case where the objects either stick together or move at the same speed, final. But even if they separate and go their separate ways, they could have lost some kinetic energy, and so epsilon would be less than 1. Now, as part of us looking at how to handle elastic and inelastic collisions, the center of mass calculation we discussed earlier comes into play. So let's see a quick example. Let's assume we have a red object, 1.5 kilograms, moving at 8 meters per second to the right, about to collide with a 4.5 kilogram object that's traveling at 4 meters per second to the right. Before we consider the collision, it's the center of mass idea is going to come into the discussion. And if we wanted to find the velocity of the center of mass, we remind ourselves that the velocity of the center of mass is a weighted average of the 8 and 4. Right? We're averaging the 8 and 4, but not outright. Right? We're taking each velocity multiplied by the mass and then dividing by the sum of the masses. This is known as a weighted average. And we would get 5 meters per second for that. Now, here are some examples of elastic and inelastic collisions and the kind of calculations that you would do. Let's have a look at a completely inelastic collision, and we'll use a one-dimensional example with the masses and velocities we saw earlier when we did a center of mass calculation. So we have the 1.5 kilogram traveling 8 meters per second, about to strike a 4.5 kilogram object moving at 4 meters per second, both objects to the right. The completely inelastic collision, we have the final state is the two objects combined as a whole, either stuck together or at least moving at the same velocity. And so when we look at our momentum conservation, we would have mass times velocity initial, 1.5 times 8 initial, and then the 4.5 times 4 initially, equal to the combined mass, the 6 kilograms, times final velocity, or all taken as a whole. And when we do that, we get the final velocity is 5 meters per second. Now, if we divide by 6, you'll see that what we actually have here is mass times velocity plus mass times velocity divided by sum of the mass, the 6. In other words, in the completely inelastic case, the conservation of momentum really is just a question of finding the velocity of the center of mass, which makes a lot of sense, right? The center of mass has to be moving at the same speed as each of the two objects that are stuck together or moving at the same speed. So that makes perfect sense. So that's the completely inelastic case. Now for the elastic case, we have that each mass final is traveling at a different velocity. I'm showing them going to the right, but we don't know unless we do the calculation. If a velocity is to the left, we'll get a negative in the result, as this is a one-dimensional problem. Now, we have the momentum conservation, same as before, mass times velocity for the initial stuff. On the final side, we just don't know the final velocities. Now, for elastic, where the objects are so-called bouncy, right, we also conserve kinetic energy. So I have the 1/2 mv squared for each mass initial and final. And that would give us a second equation, 2 equations and 2 unknowns. Now, the momentum equation, if I simplify the left, I get 30, and the right I have repeated here. But for the purpose of algebra of simultaneous equations, I'm solving for V1. Just dividing by 1.5 and bringing terms to the other side. I get 20 minus 3v2. The kinetic energy equation, I'm just simplifying a little bit, getting rid of the halves. I'm also dividing by 1.5. That would give me 3v2 squared, 1v1 squared, which I've substituted in. And the left-hand side simplifies after that to be 112. And so we get a quadratic, right? So with this method of momentum and kinetic energy conservation, we get a quadratic equation, which gives us 2 pairs of answers. After we get V2, we would back substitute and get V1. We get 2 pairs of answers. And we see that the second pair of answers is just precisely the initial velocity, so that rules that out. And we get our final velocities after the collision. Now, even though we're conserving kinetic energy, there are a couple other methods that are much more efficient instead of having to do a quadratic equation each time. One is this collision worksheet that I have. I saw this idea years ago and developed this worksheet where what we would do is we would identify the initial and final masses and speeds, velocities, and then we would calculate the velocity of the center of mass first for this method. Now, again, the center of mass calculation is the weighted average, where the masses are the weights in the weighted average formula. And we're averaging 8 and 4, and we combine these all together, we get 5 meters per second. Right? Not surprisingly, we get the velocity that we found in the completely inelastic case. Now, the beauty of the worksheet is that we want to look at what happens in the center of mass frame of reference. Right? We're in the so-called lab right now, with the 8 meter per second and 4 meter per second. And so we're interested in, for example, finding velocities of 1 and 2 relative to the center of mass, to see what the relative velocity would look like if you were running along at 5 meters per second with the center of mass. Now, the center of mass formula is that, the way I like to remember it, is the velocity of one thing relative to another, subtract the other. In other words, if I subtract the center of mass velocity from my lab velocities, I'll get the velocities of the objects as seen in the center of mass. So 8 minus 5 is 3. 4 minus 5 is -1, so I have a 1 to the left. In the center of mass, I will always see the two objects approach each other. Now here's the beautiful thing. The kinetic energy calculation, the kinetic energy conservation, is now just a bounce. Each object bounces off, almost like there was a brick wall here, bounces off with the same speed. Right? So the 1 becomes a 1, the 3 becomes a 3. And rather than algebra and quadratic formula, all we have to do now is transform back into the lab and say, well, if I subtracted the center of mass velocity to get to the center of mass frame of reference, I must have to add it to get back. So indeed, we'll take -3 plus 5 is 2, positive 2. And then I have +1 plus 5 is +6. So I have my velocities that we also found with the kinetic energy conservation. The first mass moving at 2, the second mass moving at 6 meters per second. But the beauty of the worksheet is that we only used arithmetic, no algebra. And in any case, that is an option. Now, as much as I like this option, there is a method that's a little bit better. It doesn't require a worksheet. And the arithmetic method, you can easily make a sign mistake because the arrows represent plus or minus signs. So as much as I like this, the third method we'll look at is preferred. And that's where instead of kinetic energy conservation, we conserve the relative speed. And it can be shown, for similar reasons why there was what I call the bounce step in the collision worksheet, we can convince ourselves that the relative speed is conserved. And actually, the more general formula that uses the coefficient of restitution epsilon is that the final relative speed is the initial relative speed times epsilon. Now, in the elastic case, epsilon is 1, and so we're just conserving relative speed. And the trick in doing it in a one-dimensional problem is to realize that we want magnitude of both sides. So if I start with 1 minus 2 initially, so it was 8 minus 4, right? The 8 minus the 4. To ensure I have magnitude, I have to switch the order and take 2 minus 1. And as long as you remember to do that, then this provides a simpler method. If we clean up the first equation, we get 30 equals 1.5 v1 plus 4.5 v2. If I divide it by 1.5, which I don't have to do, I'm just going to, I would have this equation coming from momentum, and if I line that up with the relative speed formula, 4 equals v2 minus v1, then I get simple linear combinations rather than the quadratic formula we saw earlier. So 24, the v1s are out. I get 4v2. I get v2 equals 6, which I then back substitute up here, and I get v1 is 2. So same answers with the both momentum and relative speed conservation, the collision worksheet, or the original method of conserving momentum and kinetic energy. Of the three methods, the preferred one would be dealing with the relative speed. It doesn't require you have the worksheet. The algebra is very simple. And that will be what we use in class. And also, if you had a restitution coefficient different from 1, you have the means to put that in here in this formula. And there we have it, impulse momentum theorem, which can be conservation of momentum if you include all of the participants in the collision. We also reviewed the elastic extreme case, where epsilon is 1, inelastic collisions where epsilon is less than 1, and the perfectly or completely inelastic case where epsilon is 0. And part of that involved, as we saw, the center of mass.